Let's go ahead and graph these two parabolas. First thing you want to do is get this into a familiar form. I actually like to move the h over. So remember that there are four definitions of a parabola. And so I'm going to write one of them. One of them looks like this. X minus h is equal to a times the quantity, let's say y minus k squared. So you could write a parabola like that. Another one could be what? Y minus k is equal to a times the quantity x minus h squared. Okay. Let's look at this one. Why don't we rewrite this one? X plus 1 is equal to the opposite of the quantity y plus 4 squared. With this form here, since there is a negative y squared, this is actually going to open to the left. So this is not a function. This is simply a graph or a set of ordered pairs. We are given the vertex, though. The vertex is here. And let's label that. The vertex is -1, -4. So -1, -4. We're in the third quadrant, and we are going to open to the left. Since we're in the third quadrant, there's very likely going to be an x-intercept. So let's find that. Let's find the x-intercept. The x-intercept occurs when y is 0. So x plus 1 is equal to the opposite of, let's say, 0 plus 4 quantity squared. So we have -16 and then subtract 1. So x equals -17. So far, we have two ordered pairs, x and y. We have the vertex, and we have the x-intercept. It'd be nice to get a third ordered pair to graph a parabola. I'm going to draw a graph that's not to scale. And I know I'm in the third quadrant, so I'm going to give myself more room for the third quadrant. So here's my y-axis. Here's my x-axis. And let's plot -1, -4. So let's say this is -1, -4. And I know it's going to open to the left. So that ordered pair is labeled now. Now, right here, I'm going to label this as -17, 0. Now, I'm only doing this because I don't have graph paper handy. And I just need a pretty quick sketch of this. Now, I need a symmetric point here. So the best thing to do is draw the axis of symmetry. The axis of symmetry is a horizontal line here. In fact, it's called y equals -4. So there's your horizontal line and your axis of symmetry. It would be nice to plot, well, it would be nice to use the axis of symmetry to be a mirror, and then we could plot a point over here, and we just have to label that. So how would we label that? I know it's -17 units because we went left 17 units, and now we need to go down how many units relative to the origin? Well, we gotta go down, -8. And there you go. You have your three ordered pairs, and that's the minimum amount that you need to graph a parabola. Now we will simply play connect the dots, and you have a parabola opening to the left as expected. There you go. You might want to pause the video and try part B. First of all, I'm going to write this in one of the definitions, and so that we could identify the vertex. So what is the vertex here? The vertex is the vertex here is -3, -7. Once again, we're in the third quadrant, but this time, because A is positive, this is going to open to the right. The vertex is right here. I'm going to skew my graph again. Oh, I should have found something first. What did I do in the previous problem? I wanted to find a second ordered pair. Because I'm in the third quadrant, it's very likely, and it's opening to the right, it's very likely that there will be an x-intercept. So why don't we go ahead and find that? Let's find the x-intercept. And of course, the x-intercept occurs when y is 0. X plus 3 is equal to 3 times 0 plus 7 quantity squared. Ooh, that number is huge. So 49 times 3, so 150 minus 3, so that is 147. Subtract 3 again, so we get x to be 144. Now let's make a t-chart. And we have -3, -7 as the vertex. The x-intercept's way out there. It's actually 144, 0. And it'll be nice to find that third point. Once again, I'm going to draw a graph that's not to scale. And let's go like this. Let's draw my y-axis over here. My x-axis is here. And I need -3, 7. -3, -7, excuse me. Why don't we call that -3, -7? And let's call this to be the x-intercept, which is 144, 0. This, what I said, was -3, -7. And we could draw the axis of symmetry. In fact, that is the horizontal line. It's called y equals -7. Oops. Y equals -7. And I need a third ordered pair, so let's call this one here. What is that? That's going to be 144, -14. And so this is the quick way of graphing a parabola. You need at least 3 ordered pairs, and one of them has to be the vertex. Oops, that doesn't look good. Let's try that again. Let's draw it through this way, and then let's make a U-turn. And through this way. That's better. Put arrows at the end. And notice both of these are not functions. They're simply graphs. These do not satisfy the vertical line test. So there you go. There are 2 graphs here. You definitely want to label your ordered pairs. Show some work on how you got them. There you go. Below is a graph, or is the graph, of a parabola with its vertex and another point on the parabola labeled. Write an equation of the parabola. First thing you want to do is probably put arrows here. You know, you got to remember there are arrows there so that those ordered pairs go on forever, forever, forever. This right here is the vertex. And according to this, since it's opening to the left, we know that this has the form x minus h is equal to a times the quantity y minus k squared. If a is positive, well, a is going to be negative. Let's find out. Why don't we use all ordered pairs here? What do I mean by that? hk, we already know what h and k are. That's -3 and -4. H is -3, k is -4. We are going to use an xy as well. So let's use -4 here. and 2 here. And I'm going to subtract an h. Subtract a negative 3 is equal to, I'm going to highlight the letter A there. And then we're going to minus what? We're going to minus a k, but k is negative, k is negative 4. And then, of course, perform the order of operations, react to this, and the only thing to solve for is the letter A. So we have negative 1 is equal to A, and then that's 2 plus 4, which is 6. 6 squared is 36. And so we get A is equal to negative 1 over 36. We need to write an equation of this parabola. So I'm going to go back to this equation here. That's going to be key. I'm going to write the equation in that form. X plus 3 minus a negative 3 is plus 3 is equal to negative 1 over 36 times the quantity y plus 4 squared. And there you go. That is the equation of this parabola. Find the first 4 terms of the sequence given by the following. Before I begin, I want to remind you that a sequence is actually a function whose domain is often the set of natural numbers. So I'm going to write the domain here. And the way we write the set of natural numbers is this double bar n. And then we write equals, and then we put a set here, a set brace. And then we start listing the natural numbers. And if you put 3 dots there, that means it goes on forever, 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 forever. Let's go ahead and find the first 4 terms of the outputs. So the outputs, you could think of the outputs being on the y-axis. But the outputs here are called a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and so on and so forth. Let's find a sub 1. We are simply evaluating an expression here. A sub 1 is equal to 43 minus 6 times 1 minus 1, which of course is 43. Therefore, a sub 1 is 43. Let's find a sub 2. A sub 2 is equal to 43 minus 6. 2 minus 1, of course, is 1. So do the order of operations. Do inside the parentheses first. And you'll notice you'll get 57. Therefore, what? A sub 2 is 57. I'm actually going to summarize it at the end. That will make things easier. So let's find a sub 3. A sub 3 is equal to the next expression, which is 43 minus 6 times 3 minus 1. And of course, do order of operations first. So 43 minus 12 is 31. So a sub 3 is the expression 31. In this problem here, you're just simplifying 4 expressions. Let's simplify the 4th expression. A sub 4 is equal to 43 minus 6 times 4 minus 3 is, 4 minus 1 is 3. So we have 43 minus 18. What is 43 minus 18? 25. Yeah, that's correct. All right, now let's write our final answers. A sub 1 is equal to 43. A sub 2 is equal to 57. A sub 3 is equal to 31. And then a sub 4 is equal to 25. Yeah, wait a second here. Something doesn't seem right. 43. Haha. 43 minus 6 is not 57. Shame on me. What's 43 minus 6? 37. That sounds better. This was an arithmetic sequence. And remember, in an arithmetic sequence, there is a common difference. So if you notice that here, D is what? D is going to be the common difference, which is negative 6, right? A sub 2 minus a sub 1, which equals negative 6. Same thing here. Notice there's a D here. D is equal to what? A sub 4 minus a sub 3, which is also negative 6. So you could see the common difference. So that's how I was able to realize that one of my numbers must have been miscalculated. I'm ready to circle that as my final answer. Now, just to remind you what a function is just a set of ordered pairs that must pass the vertical line test. So this right here is the n-axis. And then over here, this is now called the a sub n axis. So your domain values are simply these little tally marks. Like that. And of course, these keep going on forever and forever and forever. Now, if I wanted to, I could put some outputs here. I could say, here, why don't I break this up as well as I can. This is obviously a little sloppy. 10, 20, 30, 40. And so when a sub 1 occurred, well, you were up here. You were at this dot here, this output here, 43. And a sub 2 is 37, and so on and so forth. But notice this is not continuous. So there's 37, and then 31, and then what, 25. And so notice this is not continuous. In fact, if it's an arithmetic difference, it almost looks linear, but decreasing, right? And so we can't really call it linear because it doesn't represent a line. This is a function that is not continuous. And so last time you heard about continuous was something called a continuous exponential growth model or a continuous decay model. Well, sequences are functions that are not continuous. In fact, they're just little dots that pass the vertical line test. So that was just a little bit of additional information for you guys to get a better idea of what sequences are. Even though I circled the final answer, you definitely want to show this work here. So I'm going to circle that as well. There you go. Finding the first terms of a geometric sequence using an explicit rule. Well, if you wanted to, you could find, or write, I should say, the general form for a geometric sequence. So there's the general form of a geometric sequence, starting with what? N equals 1, 2, 3, and so on. But we don't really need to know the general form in this case. We just need to be able to simplify 4 expressions. So why don't we get started? Why don't we write a sub 1? And you guys could work with me and just check your answers. Remember to do order of operations first. Order of operations here says do the exponents first. So I'm really doing 2 squared first, which is 4. And we get negative 32. What do you think? Do you think a sub 4 is going to be positive or negative? So we get 8 times 8. But you have a negative in front, so it's a negative 64. Let's summarize this. Therefore, a sub 1 is negative 8. A sub 2 is negative 16. A sub 3 is negative 32. a sub 4 is negative 64. Can you figure out what a sub 5 is following this pattern? I'm going to circle all of this. Yes, I circled the final answers, but it's very important that you show some work. All right, what about the next one? Once again, go ahead and try to do this on your own, and then you could follow along to check your answers. You could pause the video if you want so that you don't see the answers right away. Once again, the order of operations says do the exponents first. So a lot of times when you're computing sequences, what you're trying to do is actually write patterns. 3 times negative 5 to the 0, so that's just 3 times 1, which is 3. This, however, says 3 times negative 5, which is negative 15. This says 3 times negative 5 squared, which is positive 75. Remember, you're doing the exponents first, okay, in order of operations. So 3 times negative 5 raised to the third power. That is negative 125 times 3. So 300, negative 375. Yeah, that looks good. And, can you check the common ratio? R is equal to a sub 2 over a sub 1, which is negative 15 over 3. It is, in fact, negative 5. Same thing if you check R equals a sub 4 over a sub 3. You'll notice that negative 375 divided by what? 75. Turns out that goes into that evenly 5 times, or in this case, negative 5. Yeah. All right. Well, oh, I forgot to summarize my numbers. I apologize. Let's summarize our numbers. A sub 1 is 3. A sub 2 is negative 15. A sub 3 is 75. And a sub 4 is equal to negative 375. The checking was just for my amusement. And so, there you go. Let's find the first 4 terms of the sequence given by this rule. A sub n is equal to the quantity negative 1 raised to the n plus 1 power times n squared for n equals 1, 2, and 3, ... So once again, here's a sequence where the domain is the set of natural numbers. And if you've forgotten, the way we write the set of natural numbers is this double bar n is equal to the set, 1, 2, 3, and so on. And then the output values of this function are merely dots. Okay, so a discontinuous function when we talk about sequences. Why don't we compute the first 4 expressions here? Let's simplify the first 4 expressions. And remember, you're doing the exponents first. So this really says what? This really says 1 times 1, right? If you're doing the exponents first, and we get 1. A sub 2. Now it gets interesting. Now we get a negative number, and then we multiply it by 4. Remember, you're doing the exponents first. So we get negative 4. What about a sub 3? Negative 1, 3 plus 1 times 3 squared. Now we have a positive 1, and then times 9. Do you think you know a sub 4 without evaluating all these numbers? So we get a negative 1 times 16, which is negative 16. And so notice it's going from positive to negative. And so a lot of times, especially in calculus, we see this right here This part right here is called the alternating symbol. So it alternates between positive or negative right there. That's like an alternating symbol there. Let's go ahead and summarize my values here. A sub 1 is 1, a sub 2 is negative 4, a sub 3 is 9, and then a sub 4 is negative 16. So these look like perfect squares, but there's an alternating symbol in front. And that is one of the ways we could write the sequences using that alternating symbol. Let's circle the final answer. Make sure you show your work. So I'm going to circle the work too. Let's see. Here are the first 3 terms of an arithmetic sequence. We're going to find the next 2 terms. And what we want to do right now is label these. So this is a sub 1, the first term of the sequence, a sub 2, the second term of the sequence, and then a sub 3, the third term of the sequence. To get the arithmetic difference, we simply take a sub 3 and subtract a sub 2. Difference means the answer to a subtraction problem. So let's figure this out. This is negative 18 subtract negative 25. So that is going to be 7. So this is actually a positive arithmetic difference. D is equal to 7. And of course, you could actually do a sub 2 subtract a sub 1, and you're going to realize you get 7 as well. So if you just add 7, you get a sub 4. A sub 4 is negative 18, add 7, and of course, that's negative 11. And then a sub 5 is equal to what? A sub 5 then would be, you take a sub 4, which is negative 11, and then add 7, which is equal to negative 4. Therefore, our next 2 terms is what? A sub 4 is equal to negative 11, and a sub 5 is equal to negative 4. That's it. Show your work. You could do the second example. You can call this example A, call this example B. Go ahead and pause the video if you want to do the second example, and do that yourself. I'm going to call this B sub 1, B sub 2, B sub 3, and of course you're trying to find the next 2 terms. Let's look for D. D is B sub 2 minus B sub 1, which equals 3 minus 9. This time it is negative 6. So how do we get the next number, B sub 4? So B sub 4 is related to B sub 3, which is, well, how about we just take away 6? That would be easier, right? So negative 3, add negative 6. That's one way to get B sub 4. So if you take away 6, you're going to realize you're going to get negative 9. B sub 5 is equal to negative 9, and then add negative 6 to it, and then you get negative 15. Therefore, what? B sub 4 is equal to negative 9, B sub 5 is equal to negative 15. Go ahead and circle your final answers, show some work. Finding the first terms of a sequence using a recursive rule. In this case, the word recursive means it really depends on previous numbers or previous steps. So suppose that a sequence is defined as follows. A sub 1 is equal to negative 4. A sub n is equal to 3 times a sub n minus 1 plus 7. For n greater than or equal to 2. And the reason why we start at 2 is because you're given a seed. So a lot of times with recursive definitions, you have to have something called a seed. You have to plant the tree before it actually grows. And then we could actually see the steps of maturation for that tree, okay? So why don't we look at those next 3 steps? Or, I'm sorry, the next 3 steps. It says list the first 4 terms of the sequence. Well, it gave you the first one. So we have the seed, a sub 1 is equal to negative 4. So what's after the seed? Well, then we use a sub 2, and then how do we find a sub 2? We're going to go a sub 2 is now equal to, according to this rule, it's 3 times a sub 2 minus 1 plus 7. But what is that? That's just simply 3 times a sub 1, which is negative 4, plus 7. And notice you're not solving anything here. Notice that you're just simplifying expressions. There's nothing to solve. You just rewrote the expression a sub 2 to be the expression negative 5. You're just simplifying an expression, and we're going to simplify 2 more. So this is 3 times what? Negative 5 plus 7. And this simplifies to be negative 8. And so on and so forth. I'm sure you could take it from here. And so notice you're just showing all the work, showing all the steps here, simply writing things pretty fast. And negative 8 plus 7. Notice you're taking the number from the previous term and using it in the calculation of the next term. So what's negative 24 plus 7? Negative 17. There we go. List the first 4 terms of the sequence. Let's summarize it. A sub 1 is negative 4. A sub 2 is negative 5. A sub 3 is equal to negative 8. And then a sub 4 is equal to negative 17. I'm going to circle the final answer, but I'm also going to circle the work as well. There we go. I'm going to evaluate some factorial expressions here. And remember that factorial here is a function. So I'm going to go ahead and write the definition of a factorial. The definition of a factorial is actually a function. So it is actually f of n, function notation, is equal to n factorial, where n is from the set. Well, let me take that back. Let me start over here. It's actually 0, 1, 2, 3. It goes like that. Basically the whole numbers. And there are 2 rules. The first one is f of 0 is equal to 0 factorial, which is equal to 1. That's the first rule. And 2, the second rule is n factorial is defined to be n times n minus 1 times n minus 2 dot 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 all the way down to 2 times 1, like that. So there are 2 parts of the definition. First of all, it is a function where the input are actually the whole numbers and the output are going to be real numbers that are actually integers. Why don't we apply some of these rules here to simplify these factorial expressions? You're not supposed to use a calculator. There's no need for that. You're actually faster simplifying these on your own. So I'm going to write 10 factorial again, 6 factorial, over 8 factorial times 8 factorial. This is equal to 10 times 9 times 8 factorial. Then we have what? Times 6 factorial. And then I'm going to rewrite it as 8 factorial here. And then I'm going to write this as 8 times 7 times 6 factorial. And let's reduce. And what do we reduce here? The 6 factorial over 6 factorial is 1. And then the what? The 8 factorial. The 8 factorial reduces to 1. So now we have 90 over 56, which isn't a big deal. No problem. Yeah, of course that reduces 45 over what, 28? And that's it. Okay, there are no common factors between 45 and 28. Let's circle the final expression. Notice you're just evaluating expressions or you're simplifying expressions for these kinds of problems. You're not solving anything, you're simply changing the way the expression looks. Let's change the second expression. Let's change the way this looks. And if you wanted to pause the video and try it yourself, feel free. You can check your answer in a little bit. Once again, we could reduce some common factors here. That reduces to 1. 2 factorial over 2 factorial reduces to 1. Notice that I'm actually crossing out very, very lightly. I don't usually like to cross out at all. This is actually 56 over 12 now. And of course, you could simplify that. Divisible by 4. 56 has what? 13, 14? And then 3. Yeah. Yeah, 56 is definitely divisible by 4 because there's 52 cards in a deck of cards. 52 cards in a deck of cards, and that's divisible by 4. So it's 14 over 3. Yep, that reduces. The final expression, let's circle your final expression. Notice you changed the way the factorials look, and you changed it to look like 14 over 3. Why do we care about factorials? Actually, factorials are very, very interesting. You may have heard of something called exponential growth, and you might have believed, well, you should believe that grows really fast. But if you look at this function very, very carefully, the factorial function grows even faster. This increases quickly to large numbers, very quickly. It actually grows faster than an exponential function, which brings a lot of curiosity to mathematics.